Okay, we're talking about real zeros of polynomials. We'll also kind of talk about some imaginary zeros as well. Um, at least it is there, could be imaginary. So when you see this first problem, hopefully you see that this is an x squared term, the highest degree, so the end behavior, you kind of know that. And you probably know how many roots it's going to have. In other words, if you were to graph this, of course this graph does actually look something like this. But clearly it has two real solutions. So wherever it crosses, so it has two real solutions there. And just in general, because this is x to the second power, you should expect two solutions. Now, they're not always going to be real solutions, or there's a couple other possibilities here, just so you know. One possibility is maybe the graph does this and touches only in one point. Technically, even that, we say one real solution, but technically it's a double root. It's the same solution twice. X equals -3, x equals -3. We don't be redundant like that, so we just say one solution. But even that technically is two solutions. It's the same solution twice. There's another case that could happen. You could have a parabola that looks like this, right, that doesn't touch the x-axis at all. This would have zero real solutions, but even that one would have two imaginary solutions. So because it's x to the second power, you should expect two solutions. It may be the same solution twice, it may be two real solutions, it may be two imaginary solutions, but you will get two solutions. So where it crosses the x-axis are the solutions. So here on this one, when you see x cubed, I'm not sure what this exact graph looks like, but I do know this. If a graph, typically a graph could look like this. It's going to start low and high, I do know that. This particular graph has three real solutions because it's to the third power, right? The highest degree term is to the third power. You could have a situation where the graph kind of does this. In that case, it would have one real solution. The other two solutions would be imaginary. You could also have a graph that looks something like this, where it just barely touches, well, it touches there, and then it just barely touches, almost like a tangent point right there. That would be considered a two-solution problem, but that one of those solutions is actually, this one's actually a double root there. So even that one is three solutions. When you have third power, you're expecting three solutions. And same thing here with fourth power, you're expecting four solutions. They're not all necessarily real. You have to look at the graph or maybe solve it to figure out if they're all real, but there could be at most four. There will be four solutions of some kind. They won't necessarily all be real. You have to look at a graph or something. This theorem basically says what we just said, which is you look at the highest degree term of a polynomial, and it's going to be the nth degree has exactly n roots. It doesn't mean they're all real, but it'll have that number of roots. Okay, complex roots or imaginary. Think of these as imaginary. So imaginary roots always come in pairs. You'll never have one imaginary solution. You'll always have them in pairs. So if a plus bi is a solution, the conjugate of that is a minus bi. It's called a complex conjugate. And they always kind of have this look to them. For example, on this one, it says find a cubic equation. Cubic means x to the third power, which means there must be three solutions. I see one solution. Here's another solution. They failed to give us the last solution, but they did tell us one of those is imaginary. What's the complex conjugate of, if that's a plus bi is 3i, then a minus bi would be negative 3i. So these always come in pairs. You're always going to find complex or imaginary solutions in pairs. And so there must be another complex one. It's going to be the conjugate of 3i, which is 0 minus 3i. And if you were to work this out to figure out the equation would be like y equals or f of x. There's going to be three factors here. And one of them is going to be x minus 5. One is x minus 3i. and one is x plus 3i. And what's nice is when you FOIL these together, I think it should simplify nicely. So we get x squared, inside outside is 0, minus 9i squared. Well, that's really x squared plus 9, right? Because I squared is really -1. And so if you want the equation, you're now just going to have to FOIL those two guys together. And so you get x cubed minus 5x squared plus 9x minus 45. And that's one equation that has those two roots and a third root, which again, because of the complex conjugate rules, imaginary solutions always come in pairs. They're always conjugates of each other. So if you had if 2 plus 3i is a solution, 2 minus 3i is a solution. This is a really intimidating kind of theorem here. It's not too bad once you kind of get used to the hang of what they're saying here. So they're saying the largest degree, we don't know what the nth degree is. It might be 5th degree. If that's 5th degree, this one would be 4th degree and 3rd degree and so forth down to 1st degree and then 0 degree here. So it's going down by ones. We don't know how many terms are going to be any particular polynomial. This one seems to have 3 at the 2nd degree polynomial. The key on this one, the thing I want you to know is that P comes from factors of a sub 0 and Q comes from factors of a sub n. In other words, let me say that differently. So this is the constant, it's a sub 0, and this is the lead coefficient. So those are the two terms. So after you see this whole big thing, if you can just identify the leading coefficient and the constant, those are the two numbers you need in order to generate all the possible rational zeros or roots. We're going to use that term synonymously with the word zeros here. So rational roots or rational zeros are the solutions, the nice rational solutions. So remember, a rational number is like a fraction. That's kind of the code word for that. Fraction of integers, it's a nice number. It might be an integer, it might be a fraction like 1/2 or something, but it's not going to be a square root of something. It's much nicer answer than that. So to find this, to list all the possibles, this is what you do. You go, okay, factors of the last term, a sub 0. So in this case, factors of 3. So in the numerator, I'm going to put factors of 3. So I'm going to put 3 and 1. Those multiply. And actually, -1 and -3 work. So I'm going to put plus or minus 3 and plus or minus 1. All these are really going to be plus or minus. And then we do the leading coefficient, and those factors go in the denominator. So those would be 2 and 1, and plus or minus for both of them. So I haven't actually listed out the possibles. So what you have to do is you kind of put all the fractions, the possibilities together here. So to list all the possible zeros, you take this fraction, you think about how many different numbers can I make? Well, let's just do this one first. So this would be plus or minus 3 over 1, or plus or minus 3, plus or minus 1 over 1, plus or minus 1, plus or minus 3/2, that fraction, and plus or minus 1/2. So I made all the possible fractions out of those 4 numbers that I could do. And so I listed them out. These are your possible rational zeros. I'm not sure if this particular polynomial has any rational solutions at all, but if it does, I will guarantee it comes from one of those 8 different rational numbers there. And so if we were, say, graphing this, let's go ahead and graph this. So 2x squared, 2x squared plus 4x plus 3. So I'm going to graph this. And you can see actually this particular function does not have any real zeros. It does not cross the x-axis. So even though these are all possibilities, none of these are actually solutions. So just because it's a possible rational zero doesn't mean it's an actual rational zero here. Let's try a different one here. So let's try this one. So find the possible rational zeros and then find all the rational zeros. So again, we want factors of the last term, so the constant there. So this would be, see, 16 and 1. I'm not going to put them in any particular order. So plus or minus 16, plus or minus 1, plus or minus 8 times 2, so plus or minus 2, and plus or minus 4. I think those are all the possible factors of 16, and then the leading coefficient is 1. So this is actually a really easy one. So in the denominator is just plus or minus 1. So if you make all the fractions that are possible there, I'm going to list them in order this time. So plus or minus 1, plus or minus 2, plus or minus 4. These are all over 1, so they just simplify. Plus or minus 8, plus or minus 16. So this is the list of the possible rational roots. Again, I don't know if this one has any rational solutions, but if it does, it will come from that list. So let's see. So x cubed, let's see where it crosses the x-axis, minus 4x squared plus 4x minus 16. Aha. So it looks like I may have found one here. It looks like it's 4 there. If you're not sure, you can always hit menu, 5, 1, go to trace. See it has a little turn in there, but where it actually crosses the x-axis is only at 4 there. So I'm going to lay down a point. So we have a solution at x equals 4. Now it says this. So I know one of my solutions is x equals 4. Find all the possibles. So don't just list out the possible, but find all the solutions. So find and then actually find all the roots, right? So we want to find all the roots. So this is, do you remember doing synthetic division? So we're going to put that solution in the box. So I'm going to put 4 in the box. I'm going to put my coefficients of the polynomial, which are here, 1, negative 4. There's no missing terms, by the way. You always want to look for that, and negative 16. You add going downwards, so this is just 1. It always just, the first one comes down. 4 times 1 is 4. You add, you get 0. 4 times 0 is 0. 4 you add. 4 times 4 is 16. All right. So remainder is 0. Remember, that's our constant, that's our x term, and that's our x squared term. So now we took this from, this was x to the 3rd power. Now we have this one down to a quadratic. This is really a quadratic here. So this is x squared plus 4. Set that equal to 0. I don't really have to do quadratic formula because there's no x term. It's just an x squared. So I'm going to subtract 4 from each side. X squared equals negative 4. Take the square root of both sides. Don't forget, plus or minus. X equals plus or minus 2i. So 2 of the solutions are imaginary. And then 2 of the solutions are, or 1 of the solutions is a real number. By the way, it said find all the roots. That means you need to find not just the rational ones, but also the irrational and or the imaginary ones. So there's 3 solutions. No surprise that there's 3. No surprise that the 2 imaginary ones came together. Those are conjugates of each other. 2i is a conjugate with negative 2i. So you always find those imaginary numbers. If they do have imaginary solutions, will come in pairs. Let's try this one. Again, pretty easy because our leading coefficient is 1. So you can just list them out. Plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. So let's graph it to find the actual rational solutions. Typically, what you should expect when it's 3rd power, like this last problem, you should expect 1 rational, nice solution. The other ones you'll have to work for. Typically, with this kind, I'll just tell you how I'll do it on a quiz or test. If it's 4th power, I'll provide you 2 that you can get from the graph. So let me just kind of write down the steps here that you would do. So to do this, you want to first list the possible rationals. List the possible rationals using the theorem. Second step, graph in your calc. Kind of an addendum to that. find any and all rational solutions from the calculator. So if you find an answer like 5.879, that's probably not rational. You want to get the nice rational solutions that come from this list of possibles. I don't want you grabbing, if there's one at 7.897, I don't want you grabbing that one. I only want you to grab the nice rational ones from the calculator. So the other ones are going to be approximations. I don't want approximations. I want the exact answers here. Step 3 would be the synthetically divide out, synthetic division, until you get a quadratic. You get a quadratic. And step 4 would be solve the quadratic. Usually that might involve, could involve factoring, but most likely it's going to be quadratic formula or just kind of solve it, set equals 0 and solve. So solve the quadratic. Typically that might be, again, quadratic formula is what I might expect. So when I give you a problem on a quiz or test, it's not going to be, if I give you fourth power, it's not going to be all nice rational solutions you can just graph from the graph. You're going to have to work for 2 of them probably. So let's graph this one and see what happens. See if that's, hopefully I did this one like that after all that build up. X to the 4th minus 4x to the 3rd minus 8x squared plus 12x plus 15. Wow, a lot of stuff going on there, a lot of solutions. Maybe these are all rational. Let's kind of see here. So menu 5.1. So you can see, looks like there's a 0, 1.7, negative 1.73. But that's not on my list of possible rationals, so I don't think that one's rational. But that one, I like that one a lot. Negative 1 is on my list of possible rationals. That's one that I want. I missed one. 1.73 is not on my list of possible rationals, so I don't want to list that one. And 5 is on my list of possible rationals, so I do want to list that one. So these other 2 solutions, 1.73 and negative 1.73, look to be probably irrational answers here. They're not on my list of possible rationals, so I'm not going to worry about those. But I got 2 from the graph. I got 5 and negative 1. So I have solutions at x equals 5 and x equals negative 1. So what you want to do is synthetically, once you find those rationals, synthetically divide them out. So I'm going to divide these out one at a time. It doesn't matter which one you pick first. It should get a remainder of 0. I kind of like doing synthetic division like this because I know it's going to work out. If I don't get a remainder of 0, I know I just made a mistake because I see on the graph it is a solution. 5 is a solution. It will have a remainder of 0 if I do it correctly. So we get 1, 5, negative 3, negative 15, negative 3, and negative 15. Phew. Remainder 0. Okay, here's the key on this one. A lot of students start over for some reason at this point. We want to get this down to quadratic. So now we want to take the other solution, take our answer. So I just kind of like take our answer, only draw over to where the remainder line is there. Just kind of stop right there when you get to the remainder and put your negative 1 in there for your synthetic division. And do synthetic division again. This is going to bring it down one more step. We're factoring out these zeros. We should get a quadratic if I do this correctly here. So again, if it works out, that's beautiful. Remainder is 0. This is a constant. This is x. This is x squared. I did, in fact, get a quadratic. So my answer here is x squared minus 3 equals 0. Again, lots of times you're going to have to do quadratic formula. In this case, there's no middle x to the first power term. So just add 3 to both sides. X squared equals 3. Take square to both sides. Don't forget plus or minus. X equals plus or minus root 3. So there are 2 irrational, which are real solutions, And there are two, 5 and -1 are also solutions there. So you have 4 solutions altogether. They're all real, and we found them by using this 4-step method, kind of listing them out, graphing on the calculator, and so forth. So list the possible rational solutions, then find all the solutions. So again, we're doing the same thing, so let's just go a little faster here this time. So, but this one actually like 4, 2, and 1, all these are plus or minus. And then 2, that's a plus or minus 1. And then plus or minus 1 and plus or minus 2. So if I put that together, it's going to be all those over 1. So that'd be plus or minus 4, plus or minus 2, and plus or minus 1. If I do factors of, I guess I could do the 1/2 here. So plus or minus 1/2. 2 over 2 is 1, I already have that, and 4 over 2 is 2, I already have that. So there's really just 8 possibilities there. Those are the possible rationals. Let's go ahead and graph this and see how many of those are actually, I'm expecting one of them to work, to be honest. The way I write my problems, typically x squared plus 8x minus 4. It looks to me like maybe 1/2 would work here. So let's just menu 5, 1. Yep, 1/2. So 1/2 is going to go in the box. And I might as well show you this now. There's going to be a little, because this is a fraction, we're going to take our quotient here and just kind of adjust it a little bit. I'll tell you when we get there. So take our coefficients 2, -1. We're not missing any coefficients. That's good. 2, 1/2 times 2 is 1. Adds up to 0, 0, 8. Half of 8 is 4. That's good. It worked out. Phew. Remainder of this. So now this is the key. When you're dividing by 2 here, you have to divide all of these quotient answers by 2 as well. So that's just kind of a sneaky thing you have to do. So whenever, if it was dividing by 3, you would divide all the quotient answers by 3 there. So I'm going to divide that by 2, divide that by 2, and divide that by 2. So I get 1, 0, and 4. This is the constant, this is the x, this is the x squared. So I get x squared plus 4 equals 0. Again, I don't really have to use quadratic formula because there's no x term there. Subtract, you get x squared equals -4. Square to both sides. Don't forget plus or minus x equals plus or minus 2i. So 2 of the solutions are imaginary. They came in a pair. They're conjugates. One of the solutions is real. It came from our list, and it came from the calculator of 1/2. We don't have to learn Descartes' rule of signs. I'll make sure the homework is reflected of that. That used to be something we have to learn how to do. We don't. That's it.